Hello everyone. So like I said, I'm going to be recording a couple of topics and posting them online as videos. And the first of those topics is Boolean algebra. In Boolean algebra, we will be using a few of the concepts from the counting, which we haven't covered yet, but we are going to be covering that in another day or two. So you should be able to understand this lecture if you just give it a day or two and go through this lecture. All right. So let's get started and look at what are the things that we are going to be covering in Boolean algebra. So the main chapter summary, this is a pretty short chapter. It does not contain more than I think about 25 slides or so. There are very few topics in here. It should be a breeze to go through this video lecture as well. All right, so what is included in the chapter? We have Boolean functions. We're going to learn how to represent these Boolean functions, and there are several ways of representing these Boolean functions, and we are also going to look at logic gates, which is a pictorial representation of these Boolean functions. All right, so let's move forward. So let's get started with first understanding what exactly is a Boolean function before we go ahead and learn about different ways in which you can represent them. Okay, so in this section, we're going to do a basic introduction to Boolean algebra, understand the nitty-gritties of Boolean algebra, how to write a Boolean expression, and we're going to define what exactly is meant by a Boolean function. So this is going to be very similar to your propositional logic and your set theory that we covered at the very beginning of this course, right? So Boolean expressions are going to be similar to your propositional expressions, and your Boolean functions are also going to be similar to your propositional expressions and functions, of course. So we're going to learn about the main identities of Boolean algebra. So we have gone through these rules or identities or laws for propositional logic. We have gone through them for set theory as well, and we're going to cover it for a third time, but in the area of Boolean algebra. All right, so we'll learn about the concept of duality and of course the abstract definition of a Boolean algebra. All right, so let's begin with an introduction to the Boolean algebra. So the Boolean algebra has some rules that we need to understand in order to know how to work with Boolean algebra. So when we did propositional logic, we dealt with propositional variables, and they could take only two values, and those two values were true or false. Right? So very similarly, Boolean algebra basically has elements which can only take the values from the set of 0 and 1. That is given right there. All right, so the Boolean algebra can only take values from the set 0, 1. So what we say is your Boolean alphabet, right? Boolean alphabet consists of only two values, which is 0 and 1, right? So if you think about the English alphabet, it has 26 letters in it, right? It has letters from A through Z. Similarly, a Boolean alphabet comes from the set containing the elements 0 and 1, right? So along with that, we also have some operators, some basic operators that basically make up your Boolean algebra. So what are those operators? Those operators are your the Boolean sum, then you have your Boolean product, and then you have your complement. All right. So we have seen in propositional logic, the basic operations were what? And, or, and negation. All right. So these are going to be somewhat in line with those operators. All right, so let's look at how these work. All right, so Boolean sum, how does that work? So if you add two ones, you get back a 1. If you add a 1 and a 0, you get back a 1. You add a 0 and a 1, you get back a 1. But if you add two zeros, you get back a 0. So this basically tells us that the Boolean sum is something similar to your OR operator, right? Or your disjunction operation in your propositional logic. So now let's look at the Boolean product. So if you multiply two ones, you get a 1. But if you multiply a 1 with a 0 with a 1, or a 0 with a 0, you always end up with a 0. So if you remember, once again, going back to propositional logic, this Boolean product looks somewhat similar to your conjunction or your AND operation. All right. And then the third important operator in Boolean algebra is your complement. So if you find the complement of a 0, you get a 1. If you have to find the complement of a 1, you get back a 0. Right? So this is similar to your negation operation in your propositional logic. So down here you have an example, right, where you have been given a Boolean expression consisting of Boolean values, and then there are operators between those Boolean values. So you can get a question like this in your exam, and you can be asked to find the value of a given Boolean expression. Right? So you are going to use the definitions of Boolean sum and product and complement in order to solve this. So what do we have here? You have 1 times 0 plus 0 plus 1 whole bar. So 1 times 0, you're going to solve the product. 1 times 0 gives you 0, right? What does 0 plus 1 give you? 0 plus 1 gives you 0 plus 1 is going to give you 1, right? And then of course you have the complement of that you need to find for the next step. Then you have a 0 as it is coming down, and then we have the complement of 1, which gives you a 0, right? And then adding the two zeros gives you back a 0 based on the definition of your Boolean sum. All right, so you're going to have some of these examples that you can work on in your textbook and also in your homework to get a good understanding or to get a good grip of how these Boolean expressions can be solved using the three Boolean operators. All right, so now that we know what values a Boolean alphabet can take, that is only 0 and 1, now let's go on and try to understand what a Boolean expression is and what a Boolean function is. All right, so you can think of Boolean expression as an n tuple, basically containing n values, and each of these values can take the value from the Boolean alphabet B. Right? So here we have an example of a Boolean expression, and we're calling it b to the n, and it contains n values, and we're calling them x1, x2, so on till xn. And each of these values of x's, x1, so on till xn, can basically take a value from the Boolean alphabet, which is your 0 and 1, 0 or 1. Okay, so now each of these individual values is called a Boolean variable. So x1, x2, so on till xn is called a Boolean variable, and b to the n represents n tuples, right? Since it contains n variables, it's called an n tuple. All right. So n tuple is made up of n Boolean variables. All right. Now it's still called a tuple here, all right, and it's not called a Boolean expression and a function because there is no operator in between each of these Boolean variables. All right, so when an operator comes into existence between these variables, that tells us what kind of operations we can perform on the set of Boolean variables. That is when you come up with a Boolean expression. And once you apply these operations, each of these Boolean expressions would basically map to a Boolean function, would become a Boolean function. All right. So since it contains n variables, we say a function from b to the n to b is a Boolean function of degree n, because your function is over n, your expression is over n variables. All right. Okay, so here down below we have an example function, and the number of variables involved in the function are just two. You see x and y. These are the only two variables in the function, right? Now each of these variables can take values from the set 0 to 1, right? So since there are only two variables, we say this is a Boolean function. F is a Boolean function of degree 2. All right. Now, so on the right hand side, what we have is the Boolean expression. All right, Boolean expression over the two variables x and y. Right. What does the Boolean expression read? It reads x times y bar plus x bar times y, and then you're complementing the entire expression, so you're getting whole bar. Right. So this would when you basically give x and y different values, this expression would evaluate to either a 0 or a 1, right? So now let's go back to our propositional functions and propositional variables, right? So when you had a propositional expression that consisted of multiple variables, right? Propositional variables. So so basically, depending on how many variables are in the expression, you basically come up with all possible combination of values that these variables can take, right? And then basically evaluate the function based on each of these combination of values, right? So when we had two propositional variables, what were the possibilities? True, 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 false, false, true, and false, false. Very similarly. So what are the possibilities of the values that x and y can take here in Boolean algebra? You can have 1, 1, 1, 0, 0, 1, and 0, 0. Right? So now at this point, if we were to add another variable, let's say z, to the mix here, then something similar that we covered in propositional logic would also happen here. So if we were to add z, then you'll have the same set of values for x and y when z is all zeros, 0, 0, 0, and 0. And then the same set of values of x and y when z takes the value 1, 1, 1, and 1. Right? So we're going to see an example of that in I think the next couple of slides very soon. All right. So we're going to see a Boolean expression that contains 3 Boolean variables and not 2, as in this case. All right. So here is the example of a Boolean expression that is using 3 Boolean variables, right? X, y, and z, right? And what does the function look like? X times y plus z bar. right? So here is a question that asks you to find the values of the Boolean function represented by x times y plus z bar. So how would we do that? So first we have to find all possible combinations of values that can be taken from the Boolean alphabet by x, y, and z. Right? So this is very similar to the truth table that we built in propositional logic, right? So here is a table that we have, and you have x, y, and z, right? So how exactly do we basically fill up this table? So you basically have one, let's take y and z, right? So you have 1, 1, 1, 0, 0, 1, and 0, 0 until there, okay? And then you're going to put all ones in front for the values of x, okay? And then you're going to repeat the same values for y and z, 1, 1, 1, 0, 0, 1, and 0, 0. But then this time repeat with zeros, all zeros for x. Okay, so that's how you usually find all possible combinations, all right, of values for 3 variables. Now, if it were 4 variables, what would happen? You're going to repeat this entire section twice, all right? Once with all ones in front of it, and then the repeated section with all zeros in front of it. Okay? All right, so now you're going to evaluate the value of the function x times y plus z bar, and you're going to build it up by finding the operation between 2 variables at a time and building it upwards. So the first thing you do is find the values of x times y, then you're going to find the values of z bar, and then you're going to put those two together to give you the actual function x times y plus z bar. Now let's look at equality of 2 functions and some operations that can be performed on functions. All right, so why do we say we can actually perform operations on functions? Because each function actually evaluates to either a 0 or a 1. Essentially, it's also a Boolean expression. All right, and when we are actually adding together 2 functions or multiplying 2 functions, what we are essentially doing is finding the product of the 2 expressions represented by these 2 functions. All right, so let's start by defining equality of 2 functions. So when do we say the 2 functions f and g, each containing n variables, are equal? Right? When each of them evaluates to the same value, right? We know here that let's take f as a function. It's either going to evaluate to a 0 or it's going to evaluate to a 1. All right, so whenever f evaluates to 0, right, for all the values of b1 to bn, if g also evaluates to 0 for the same values for b1 through bn, then we say f and g are equal, right? The same way, when f evaluates to 1 for a given set of values for b1 through bn, if g also evaluates to 1 for that same set of values b1 through bn, then we say the functions f and g are equal, right? And once again, do not forget, b1 through bn are each of them represent a variable, Boolean variable, and they can take values from the Boolean alphabet, which is going to be either a 0 or a 1. All right, now let's move on to the next definition. So how do you find the complement of a Boolean function? Right? So once again, like I said, a function either evaluates to a 0 or a 1. Right? So once we find out what it evaluates to, if f evaluates to 0, then we know that f bar would evaluate to 1. Okay, and if f evaluates to 1, then we know that f bar would evaluate to a 0. Okay, so that's how you define the complement of a Boolean function, right? So now how do you define the sum and the product of two given Boolean functions? Right? So let's take example of two Boolean functions, two general functions f and g, right? And each of them have the same degree n. That's important. Each of them have basically the same number of variables going into each of the functions, right? That's only when we can find the sum of the two functions, or we can find the product of the two functions. And how is it defined? So f plus g of the function is defined as, first find what the function f evaluates to, then find what function g evaluates to for a given set of values x1 through xn, and then find the sum of those two values. Okay, the same way for the product, first evaluate what function f evaluates to, what function g evaluates to for all the values of x1 through xn, put into the function x and put into the function f and put into the function g respectively, and find the product of these two resulting values, and that's going to be the product of two functions. All right, so let's now try to see how we can understand how to find the number of Boolean functions given the degree of the Boolean function, right? That is, how do you find out how many Boolean functions are possible given the number of variables that are being fed into the Boolean function, right? And you're going to learn about this in just about a day or two when we're going to cover the product rule in counting. But assuming that you're going to look at this lecture after going over the counting slides, so let me go ahead and explain. So using the product rule, all right, there are 2 to the n different tuples of zeros and ones. Right? So let's assume it is a Boolean function of degree 2. That is, there are 2 values that need to be filled in. So how do we fill in each of the values? You can either fill in with a 0 or a 1. You can either put in a 0 or a 1. So the first place can be filled in 2 ways. The second place can be filled in 2 ways. So that's why we have 2 to the 2 possible ways of finding the number of tuples. All right. Now, it's the same way if you have n tuples. So this is when you had a 2 tuple, the number of ways of finding the different possible n tuples is to the 2 to the 2. So you can think of it as generalizing. If you had n tuples, then how many different n tuples would you get? It's going to be 2 to the 2 to the 2, so on n times. So that's going to be 2 to the n different n tuples. All right. Now, adding to that, each of these n tuples is going to either evaluate to a 0 or a 1 when applied to a function. Right? When you apply a function onto the given 2 tuples or the n tuples, it's either going to evaluate to a 0 or a 1. Right? So each of these 2 to the n have 2 ways of mapping. All right? They can either, each of them can either map to a 0 or map to a 1. All right? So once again, by the product rule, right, for each of the n tuples, the first tuple has 2 to the n possible ways. The second one has 2 to the n possible ways, and so on. So by the product rule, we have 2 to the n total number of Boolean functions possible with a degree of n. All right. So here down below, you have an example of 2 variables into the being fed into the tuple. So it's a 2 tuple. So the degree is 2. So what are the possible number of tuples? You have 4 tuples, right? You have 2 to the 4 tuples, 2 to the 2 tuple, that is 4 tuples. And so we see how many rows here? There are 4 rows. Okay, now now how many functions are possible? 2 to the 2 to the n. All right, so what is 2 to the 2 to the n? It is going to be 2 to the 4, which is going to be 16. So you can actually come up with 16 functions. All right, 16 different functions in between those two Boolean variables. Right? So just like the identities that we went over in set theory and in propositional logic, there are also identities for Boolean algebra, and a lot of these are going to be very similar to the ones that we have covered in set theory and propositional logic. All right, so for example, the first one that you see is similar to your double negation law. So this is called the double complement. So complement of a complement gives you back the value of the variable, right? So the next one is called the idempotent law. If you take a variable and add it to itself, or basically do a product to itself, you get back the same variable. Then you have the identity laws. That is, if you add a 0 or multiply 1 to a Boolean variable, you get back the same variable. Then there is the domination law that says that if you add a variable and then if you add a variable to 1 or multiply it with a 0, then you get back either a 1 or a 0. The next one that we have is the commutative law. That is, you can add two variables in any order or multiply them in any order. And then you have the associative law that tells you that if you add two variables and then add the third variable, or you add the second and the third variable and then add it to the first variable, it's the same thing, and the same holds for the product as well. Now the next one is called the distributive law, right? So then we have the De Morgan's laws, exactly as in your propositional logic and your set theory. All right, you have your absorption law, then you have your unit property and zero property. Okay, so so all of these identities basically tell you that you can actually prove some of these identities using a tabular approach. We are not going to have logic-based proofs in Boolean algebra. We have already done that in propositional logic and in set theory, and it's going to be very similar. So we're not going to do it once again here. So most of the proofs that we do are going to be using a tabular approach, where you build the table with all the possible values that the variables can take and show the left hand side of an identity is equal to right hand side to prove that identity. Okay, so here is an example of how you're going to prove identities in Boolean algebra. So like I said, we are not going to be using the identities to prove the left hand side is right hand side here. Instead, we are going to use the tabular approach, right? So we are going to build a table, and we are going to build a table for all the variables that are in the identity. All right, and then we're going to basically jot down all possible combinations of values that can be taken by these variables, and then we're going to build the identity by combining two variables at a time, both on the left hand side and on the right hand side, and show that they're equal. Right, so with the example at hand here, we need to prove that the left hand side here says x times y plus z is the same as xy plus xz. right? So in here in the table, we come up with all possible combinations of x, y, and z, right? That's what we start off the table with. And then we are going to build the table, right? By adding one operator at a time. So we're going to do y plus z first for the left hand side of our equation here, right? And then we are going to basically multiply x times y plus z in here. And also we are going to do x times y, and we can do x times z, and then add both of these to give our right hand side, which is x times y plus x times z. So basically we need to show that this column is equal to this column for every combination, once again, for every combination of x, y, and z, right? And as we can see, right, for these two columns, the values are equal, right, for every combination of x, y, and z. And that's how we go ahead and show that the identity, the given identity, the distributive law is valid using a table. So in the next part of Boolean algebra here, we are going to learn about how to represent Boolean functions. All right. Specifically, we are going to learn about sum of products expansions. All right. And there is going to be some relationship here with the DNF and CNF that we covered in propositional logic. Right. I want you to go back and check what DNF and CNF stands for. Right. So DNF was our disjunctive normal form, and CNF was conjunctive normal form, right? So we actually did a small section on how to find DNF and CNF for a propositional expression, right? So we're going to look at something similar in here, and we are going to learn about the concept of functional completeness. Let's take a look at how to find the sum of products expansion of a given function. All right. So let's consider two example functions, f of x, y, z and g of x, y, z. And the values of these functions for all possible combinations of x, y, and z are given to us in the table here. All right. In the table on the right hand side. So we are basically going to look at how to find the sum of products expansions. All right. So how do we do that? In order to represent the function f using the sum of products expansion, we'll have to basically go through the column of f and see where 1 appears in the column. So we see a 1 right there, right? And there is no more 1 in the column of f, all right? So there is only going to be one term in the sum of products expansion that represents the function f, all right? Now we are going to look at what x, y, and z for that corresponding row are like, right? So if you see a 1 under x, it's going to the term is going to come down as x, right? But here, since there is a 0 under y, it's going to be represented as y bar, all right? Since there is a 1 under z, it's going to be represented as z, as z. So the term that we have is x y bar z, all right, in order to represent the sum of products expansion of the function f, all right? So now let's look at the other function that's been given to us, the function g. So how do you find the sum of products expansion for the function g? So let's take a look at the column for g. Let's start by looking at where 1 appears. So we have a 1 right there, and then we have another 1 right there, right? So now we are going to look at what are the values of x, y, and z for those rows. Okay, so let's look at the first time one occurs. So we have x is 1, y is 1, z is 0. So this is going to be x times y times z bar. All right, and what is going to be the other term? The other term in the expansion is going to be, this is going to be x bar times y times z bar. All right, and both these terms have to be added. All right, so once again, since x is 1, y is 1, the terms are going to come as they are, and then since z is 0, it's going to come as z bar in the sum of products expansion. This is going to be the first term. In the second term, where 1 appears under the column of G, so you see a 0 under X, you see a 1 under Y, and you see a 0 under Z. Therefore, you have X bar to represent a 0, Y to represent a 1, and Z bar to represent another 0. Alright? So that is the basic principle that you follow in order to find the sum of products expansions. So you're going to first start by looking at how many ones there are under the function column, and there will be a term to represent each of the rows where there is a 1 in 1 under the function column. Okay, and each of them is going to be added. Since there is only one such term for function f, you only got one term. Since there are two ones for function g, you get two terms in your sum of products expansion. Here are some of the definitions that we basically learned about with the example in the previous slide. All right. So what exactly is a literal? A literal is a Boolean variable or its complement. Let's say x is a Boolean variable. Both x and x bar are both literals. All right. Now, what exactly is a minterm? Right? Minterm of Boolean variables. Let's say there are n Boolean variables, x1, x2, so on till xn. Basically, is going to be a product of the literals which come from these Boolean variables x1 so on till xn. Right? So it's going to be a product y1 so on till yn. Okay, and y1 can either take the value of x1 itself, right, or any of these yi can take the value of xi itself, or it can take the value of xi bar. Right? So exactly like the example we looked at in the previous slide. Right? So a minterm is going to have all the variables, all right, all the variables that are that basically go into producing that function. Okay, and there is going to be one literal to represent each of the variables. So we say one literal because it can be either the variable itself or its complement. All right, so what is another thing that we learned here? The minterm basically evaluates to a value 1 only if each of these y1, y2, yn so on evaluate to 1, right? And how is that possible? If that's possible if your y1 is equal to x1 or yi is equal to xi whenever xi is equal to 1, and yi is equal to xi bar whenever xi is equal to 0. That's the only way this is going to be possible. All right, so the sum of all of these minterms gives you what is called the sum of products expansion. All right, so the sum of these minterms gives you the sum of products expansion, and this is representative of the disjunctive normal form of the Boolean function. All right, so once again, I want you to go back and look up how we found the disjunctive normal form of a propositional expression. right? Or a propositional function, right? I want you to go back and look at that, and this will basically make more sense at that point of time. Here is another example of how to find the sum of products expansion of a given function. So the function given to us is f of x, y, z is x plus y times z. All right. So in order to find the sum of products expansion, we have to do two things. The first thing is come up with this table that represents the given function, right? How would you do that? First, see how many variables do you have in the function. You have 3 variables in the function. So you are basically going to produce all possible combinations of these variables x, y, and z in 3 columns, the first 3 columns, right? And then you are going to build the function, all right, one by adding or basically adding one operator at a time. So you get x plus y, and then you found z bar here, and then finally you have evaluated the function, the actual function, which is x plus y times z bar. All right. So once you have this table, what do you do next? You're going to look at the function. So this column represents your function f. All right. And you're going to see where all there is a 1 under this function column. So there is a 1 right there. There is another 1 right there, and there is another 1 right there. So there are 3 ones under your function column. This tells us that there are going to be three minterms in your sum of products expansion, right? So you are going to look at the literals that will make up your minterms. So what is going to be in the first minterm, right, is going to come from that row. What is going to be in the second minterm is going to come from that row, and then what is going to be in your third minterm is going to come from that row, right? So as we see here, for the first minterm, you're going to take x, y, and z bar to represent a 0 under z, okay? So that's how you got the first minterm, x, y, z bar. And how do you get the second minterm? So you have a 1 here, and then a 0 and a 0. So you have to just take the literal as it is for the first term. So x, and then you take y bar and z bar to represent the other two terms. So that's how you get x times y bar times z bar to get the second minterm. Now let's look at the third row that gives you the third minterm. So x is 0, z is 0, and y is 1. So that's going to give you x bar times y times z bar. That is the third term in your sum of products expansion. Alright, so there is yet another way to find the sum of products expansion given a function. Alright, so this was the function that was given to us. And this way is to use the Boolean identities that we looked at a couple of slides back. There was a whole set of identities listed in a table, right? So we're going to use some of those identities to come up with the sum of products expansion. Alright, so how do we do that? So let's say first you have the function, alright, that is x plus y times z bar. So you're going to open up the function until you basically have sum of products. It's you have the literals in the form of sum of products. So you have x times z bar plus y times z bar by opening up the brackets, right, and using your distributive law. Now what we notice here is that one of the variables is missing in the first term and one of the variables is missing in the second term, right? So which variable is missing in the first term? There is x, there is z, but there is no y, right? So let's put a 1 in the middle to represent wherever it is in order to represent the y. All right, because just multiplying, we know that multiplying any variable with 1 gives back the variable itself. All right, so we're going to put a 1 in the y's position, and in here we're going to put a 1 in the x's position because x is missing from this term. All right, so we are using the identity law and putting a 1 basically, or multiplying the term xz bar by 1 because it's going to just give you back xz bar based on the identity law. Now what are you going to do next? You are going to use the unit property, right? You're going to use the unit property basically that tells you that take any variable and add it to its complement and it is going to give you back 1. All right, that is, for example, y plus y bar is equal to 1, z plus z bar is equal to 1, and x plus x bar is equal to 1. All right, now let's look at the first term. All right, and you're going to replace 1 with this unit property with the missing variable in this term. So the missing variable was y, so you're going to replace 1 with y plus y bar. What about the second term? So you have a 1 here, and what is the missing variable in here? X. So you're going to replace it with x plus x bar. All right, so now once again use the distributive law and make sure that you have it in the most expanded format. So you have x times y times z bar plus x times y bar times z bar, and then from the second set you have x times y times z bar plus x bar times y times z bar. All right, so if you notice closely, you have two of the same terms in here. So you have x times y times z bar once there and x times y times z bar again there. All right, so we know from idempotent law that a variable added to itself gives back the same variable, right? So if we take x and basically add to x itself, then what you get is going to be x. All right, so similarly, if you add x times y times z bar and add it to x times y times z bar, you're going to get back x times y times z bar. So just take away one of the terms here, or basically replace two of these terms with just one x times y times z bar, and then write down the other two terms as they are. All right, right here and right there. Okay, so the other two terms come down as they are. So now what we are left with is our sum of products expansion of the given function. Right? So if you go back to the previous slide, you're going to see that using the tabular approach gives us the very same sum of products expansion as we got here using the Boolean identities. All right, so I want you to be prepared that in the exam you could be asked to find the sum of products expansion of a given Boolean expression using a table, and you should also know how to find the sum of products expansion using the Boolean identities as well. All right, so the next concept we are going to look at is functional completeness. All right, so let's try to give a basic definition of functional completeness. All right, so we know that any Boolean function that we take can be represented using the three basic Boolean operators, which is your product, plus, and addition, and your complement. All right, and therefore we say the set of operators containing the product, the sum, and complement is functionally complete. All right, so in other words, a set of operators which can let you completely define any Boolean function is called is said to be functionally complete. All right, so now let's look at some other examples. All right, so the set containing only the product and complement is also functionally complete. Why? Because here is an example that shows how to take an addition and convert an addition between two variables and convert it into an expression that only contains a product and the product and the complement operators being used. right? So basically this tells us that you can convert an addition that occurs in any Boolean function and basically make it look like a product and complement operators. All right, so what we understand here is just the product and the complement itself are functionally complete. All right, very similar way, we can also show that just the sum operator and the complement are functionally complete. And how do we say that? So you can express a product between two Boolean variables as basically a sum of complements and then the complement of the whole thing again. All right, so a product between two variables can be represented without using the product symbol, right, or without using the product operator. And therefore we say that just the set containing the sum and the complement are said to be functionally complete. All right, so now let's look at a couple of other operators. All right, so far we have only looked at the addition operator, the negation operator, and the product operator. All right, so here we're going to address two more operators. They're called the NAND operator and then the NOR operator. All right, so the symbol used to represent a NAND operator is just a straight line, right? A straight vertical line. And the symbol used to represent a NOR operator is a downward pointing arrow. Okay, so how exactly is the NAND operator defined, right? So NAND operator is defined as using these following rules. So 1 NANDed with 1 gives you 0, right? But 1 NANDed with 0, 0 NANDed with 1, or 0 NANDed with 0 is all equal to 1. So if you look carefully at the rules for the NAND operator, what you see is it's basically the complement of your AND operator. Okay, so whenever you have two ones, you get a 0. Everywhere else, you are going to see that the operator evaluates to a 1. All right, so basically NAND is nothing but your negative AND operator. All right, so now we can see that just a single NAND operator is good enough to represent any Boolean function, right? So here is basically equations to show that the complement of a variable can be represented using the NAND operator. The product of two variables can be represented using NAND operators. And since we saw that the product can be represented as a sum in the previous step, so even the sum of two variables can be represented using the NAND operator indirectly. All right, so NAND operator, just the NAND operator can represent your complement, your product, and your sum, right? So the set containing just the NAND operator is said to be functionally complete. All right, very similarly, now let's look at the NOR operator. So let's look at the rules for the NOR operator first. All right, so what do the rules for the NOR operator tell us? So if you have two zeros, the NOR of two zeros is a 1, but the NOR of 1 and 0, the NOR of 0 and 1, and the NOR of 1 and 1 is 0, right? So once again, look carefully. NOR is nothing but your negative OR operator, right? That means it's basically what you get when you find the OR of two variables and complement it. Okay, so NOR operator is your negative OR operator. All right, so the set of just one operator containing the NOR is said to be functionally complete. Very similar to the previous case, you can basically show that the complement of the variable can be represented just using the NOR operator, and similarly the product of two variables and the sum of two variables can also be represented just using the NOR operators, right? And therefore the set containing only the NOR operator is said to be functionally complete. Alright, so finally we have come to almost the end of Boolean Algebra, the chapter. And the last thing we're going to learn about is logic gates. So logic gates have a lot of importance in computer science and also in electronics and communication, right? So logic gates are the basics that you need to know in order to design circuits, all right? And we are going to look at how to build these logic gates based on Boolean functions in the next few slides. In the next few slides, we're going to learn about some of the basic logic gates, that is the AND gate, OR gate, and the gate that represents the complement. And then we're going to look at the combinations of these gates and how you can build the Boolean functions that we looked at in the beginning of this chapter using these logic gates. And then towards the end, we're going to show how circuits can be built based on these gates. Alright, so we are going to look at logic gates. These logic gates form the basis for more complicated circuits and for chip design. Alright, so that is used in electronics and communication and in computer science going forward. So what exactly is a gate? A gate takes in either one input, two input, or more than two inputs and basically produces a single output for you, right? So let's take a look at what are the primary gates that you need to know about in logic, right? So the very first gate here is called the inverter, and this represents the complement operator, right? So inverter basically performs the complement function, the complement Boolean function, right? So it takes a variable x and produces x bar. All right, so the next gate here is called the OR gate. All right, so it basically takes two variables as input and it produces an output which is going to be the OR of the two variables, or in our Boolean algebra it's going to be the sum of the two inputs. All right, and then the third kind of gate is our AND gate. Okay, so it takes two inputs and basically produces an output which is representative of our Boolean function product. All right, and it's also representative of the AND function from propositional logic, and that's why it's called the AND gate. All right, so like I said before, you can have these gates take any number of inputs possible. All right, here is an AND gate that is taking multiple inputs and producing basically an AND of all of these inputs. And here is an example of an OR gate which is taking multiple inputs and producing an output which is representative of the function which is going to OR all of these inputs. So you can combine several of these gates together and produce much more complicated circuits or combinatorial circuits. All right, so here we have an example that basically produces a complicated function which is representing your product of x times y plus x bar times y. And how is it produced? First you give inputs x and y to an basically an AND gate, and that gives you x times y. Then you basically put x through an inverter that gives you x bar, and then you pass x bar and y through another AND gate, and that gives you x bar y. Now you pass the output of the AND gate here and the AND gate here and into an OR gate that gives you x times y plus x bar times y. Alright, and there are two different ways in which this can be done. So in here what you notice is the inputs are being repeated twice. Alright, but you can actually use the same inputs and basically come up with the complicated circuit, but you basically use the same input and give it as the input to all the gates that need an input from that variable, right? So this also produces the same function as the one above. Alright, so here are some exercises that I want you to work on and produce the gates. Alright, so the first one is it's taking x and the sum of x and y. Alright, so you need a OR gate to represent this. Alright, and then the output of this has to be combined with the x bar. So how do you get x bar? By passing it through an inverter first, right? And then the output of the inverter and the output of this OR gate have to be passed into an AND gate to give you the whole function, right? So let's look at the solution. So you're passing x and y, right, into an OR gate here, right, to represent x plus y first. You're passing x through an inverter to give you x bar. Then you're passing the output of these two into an AND gate, and that gives you x plus y times x bar. Alright, so let's look at the next one. So you have x bar, right? So you are passing x through an inverter to give you x bar. All right, what is the second part here? So you have y plus z bar whole bar. So first thing you need is the innermost one, which is your z bar. So first take your z, pass it through an inverter, that gives you z bar. Then take the y and add it to z bar. So take the y, add it to z bar using a OR gate, right? So that gives you the sum y plus z bar. But we also need to represent that outer complement, right? And that, how are you going to get that? You're going to get that by passing y plus z bar right here through an inverter, right? And that gives you y plus z bar whole bar. All right, and then you're going to basically pass this output here, right, and x bar through a AND gate, and that is going to give you your final answer. That is going to be x bar times y plus z bar whole bar. Okay, so the last one, I'm going to leave it up to you. If you have a question, you can come by and ask me later on. All right. Now we are at the end of the chapter here on Boolean algebra, and I'm going to post these slides, and I'm also going to post the homework on Boolean algebra pretty soon, by the end of this week. And I'm also going to record the slides on graphs next, all right, and put it up so you have the time to basically go through it much before your finals. All right, I'm going to make it available to you probably by the end of this week. All right, so for now I want you to go through these slides and learn about Boolean algebra. All right, and if you have any questions, please come by and ask me or bring them up in class. And if you are working on any problem that you want to discuss, I would say please bring it up in class and we can try to solve it there, and it's going to help the other students out as well. All right. Okay. All right then. Have a nice day.